In this video, I wanted to talk about, well, what happens when the degrees of the polynomials in our rational function are actually equal to one another. In the last one, we talked about what happens when the bottom is bigger, and that always results in a horizontal asymptote at y is equal to 0. But as the guidelines say, if the degree of the numerator is equal to the degree of the denominator, it says that the horizontal asymptote is the equation y is equal to the ratio of the leading coefficients. Now, this is not a mathematical expression. This is just kind of my way of trying to explain how I consider finding the asymptote. So that's what I wanted to say in this particular case. But in the same way, let's try to take the same approach and try to find the vertical asymptote, the horizontal asymptote, and the x-intercepts all, and let's try to do it in the same order that I was doing in the other videos, just so there's a little bit more consistency about my process. Because I'm solving so many different things that I'm sure it can be easy to lose track of what I'm doing. So let's start with the vertical asymptotes. Those can always be found by taking the denominator and setting it equal to 0. So 2x squared plus 4x equal to 0. And factoring this will help me solve. So here we have a common factor of 2x, which would leave me with x plus 2. And so this will result in two different zeros. X is equal to 0 and x is equal to negative 2. And when there are two, when there's two distinct zeros in my denominator, that just means there's going to be two unique vertical asymptotes. So this graph will should actually have two vertical asymptotes at both 0 and at negative 2. And if we're trying to sketch this, I would always start by sketching those vertical asymptotes. So one is going to occur at x is equal to 0, and another at negative 2. And I'll go ahead and label my graph as I'm going. Oops, you could not see what I was drawing. So the thing that's different about when the degrees are equal is what's happening to the horizontal asymptote. And this is going to be a little bit different. And basically what you can do is if you just take a ratio of when it's equal, if you take the direct ratio of those leading terms, that will give you the equation of the horizontal asymptote. So if I do exactly that, I would have y is equal to x squared over 2x squared. Notice that, of course, when it's an equal degree, the x squareds will just cancel each other out, and all that will leave me with is a ratio of the leading coefficients. And that's what I mean when I say this. When the degree of them are equal to one another, the horizontal asymptote is y is equal to a ratio of the leading coefficients. It's sort of like how the y-intercept was a ratio of the constant terms. The horizontal asymptote is a ratio of the leading terms. And again, there's a reason why this is true. I'll try to explain that here in a minute. And this would be my horizontal asymptote in this location. And it's slightly higher. It's not at 0, it's actually at 1/2. And whenever you have an equal degree of your polynomials, it's never going to be at 0. It will always be at some other location. And what I wanted to actually do is let's check, because we did an example a couple videos ago where we had a horizontal asymptote going through 3. Let's see if this is consistent with what we had from before. So notice, going back to example number 2, this one had the asymptote there at y is equal to 3. If you're looking at this kind of under this new lens, notice that if we look at the leading coefficients here, the leading terms, we had 3x over x. And of course, if you take a ratio of 3 to 1, right, that gives you exactly 3. That's the algebraic way that you could figure this out. And it's a little bit harder to do because you have to know exactly where to look, but it's all about that ratio of the leading terms for a horizontal asymptote. Now for the y-intercept, that's always going to occur at by plugging in 0. So if I plug in 0 here, that's going to give me, notice actually 0 is undefined here because we have a vertical asymptote at 0, meaning that this actually will not work. And so our conclusion is that it has no y-intercept because it has a vertical asymptote at 0. And of course you can't divide by 0, which you would get if you plug in 0 down there. And if we're looking for the x-intercepts, that's always comes from setting the numerator equal to 0. So if I take x squared minus 2x minus 4 and set that equal to 0, that should give me my, so again, this was the y-intercept, there is none, and this would be for finding the x-intercepts. And this is a quadratic which appears to be have no rational zeros and be a prime when using only rational numbers. But I could always use the quadratic formula on a quadratic to see, well, what are the zeros of this equation? So let's just check real quick. That would give me negative b plus or minus b squared minus 4ac, which would be minus 4 times 1, which is plus 16, all divided by 2 times a. And so that would be 2 plus or minus rad 20 over 2. And rad 20 can be reduced to, because it's 4 times 5, and the square root of 4 is 2, can be rewritten and simplified to 2 root 5. And we could even reduce this a little bit farther by dividing by the common factor of 2. 2 over 2 is 1, and 2 root 5 over 2 is just root 5. So 2 plus or minus root 5. And basically we could get those x-intercepts. In this case there's going to be 2 because it's degree 2, but they are irrational zeros, which is fine. It just means it's a little bit uglier. And of course you could use your calculator to find those as well. So let's, now that we've figured all this stuff out, let's just see if all of the information that we found was accurate by graphing it in our calculator. So we had x squared minus 2x minus 4 divided by 2x squared plus 4x. And let me make it a bit bigger. But notice that this rational function, going from left to right, we've got this sort of like, they sort of look like elbows too, if you ever hear me use that explanation. But we've got kind of this elbow, or cliff, which they sort of have. There's actually this weird thing in between the vertical asymptotes where it does a little bit of a noodle shape or something, and then it kind of comes back to another cliff over here. And notice that it does have x-intercepts right here and right here, and those should be those two locations, 1 plus root 5, or sorry, 2 plus root 5 and 2 minus root 5, which are the exact values of those intercepts, assuming I did not mess that up. So let's go ahead and graph all of this. But basically we have an x-intercept right there, and in between the asymptotes, notice that the vertical asymptotes, like the curve should always, explode upwards towards the vertical asymptotes. That's kind of the point. And the only thing we don't know is whether it's going up or down. And the graph can help us see really easily whether it's going up or down on either side. And then on the right side towards 0, from the graph, we can see that it's going down really rapidly, and it's crossing somewhere over here, which we can't tell. And also, another thing that if you're just eyeballing the graph, it can be kind of hard to see, well, where is the horizontal asymptote? Like, if you didn't know any better, you might think that the horizontal asymptote was at y is equal to 0, because over here it kind of looks like the other ones did, where it's sort of traipsing downwards, getting closer to the x-axis. But notice on the right-hand side, it actually does appear to cross and go over it because of this little bit right here. And so, obviously being able to check the horizontal asymptote using the method, that I was describing earlier is helpful because it helps you determine where that horizontal asymptote is without having to just guess. So let's finish our graph, because also on the left-hand side of the second vertical asymptote, it kind of went in between it, sort of like this. And if you're trying to create a sketch or graph a rational function, again, this is not a graph. This is just sort of a rough sketch of what it looks like. But it shows all of the important traits, like what's happening as we head towards infinity, what's happening as we head towards 0, towards the various asymptotes. And basically it's kind of like exploding, going up, going down, and doing all this sort of crazy behavior. But again, the more asymptotes you have, the more splits you're going to have, and the more kind of gaps and breaks in the function that it will incur.